Ask an artificial intelligence to compose a sonnet in the style of Shakespeare about a lonely astronaut, and it will deliver. Ask it to explain the theory of general relativity as a bedtime story, and it will oblige. These large language models just get human language, like it's second nature, a smooth flow of meaning and connection. But not many people realize that the seed for this tech was planted before and beyond Silicon Valley labs and tech giants. In fact, the obscure world of theoretical physics had a huge role to play in the development of thinking that would eventually lead to AI. The story of modern AI is in many ways the story of how a deep physical principle, the universal tendency of systems to seek a state of minimum energy, was repurposed to model the mind. It is a narrative of unexpected connections, where the quest to understand the frozen, random state of a useless material provided the blueprint for machines that can learn, remember, and even create. The journey begins not with a bit or a byte, but with a puzzle of frustrated atoms. The evolution of modern artificial intelligence remarkably mirrors a fundamental physical principle: the universal drive of systems toward minimum energy states. This parallel means that the early studies of materials provided the conceptual framework for machines capable of learning, remembering, and even generating new ideas. This is the story of how physics gave birth to AI. In the mid-20th century, physicists studying certain alloys such as iron, atoms scattered randomly within a grid of copper, encountered a strange new state of matter. At high temperatures, these materials behaved predictably, but as they cooled, they did not settle into the orderly, aligned state of a common magnet. Instead, their atomic magnets, or spins, froze in a completely disordered arrangement. They became what is known as a spin glass. The core of this behavior is a concept called frustration. Imagine a small, tightly knit community where each person has fixed preferences about how to orient their house. One person might want their door to face their neighbor's door to the east, but turn their back on their neighbor to the west, who in turn has their own conflicting desires. In a simple magnet, everyone agrees to face the same direction, achieving a state of low-energy harmony. In a spin glass, the random and competing interactions mean no single arrangement can satisfy everyone. The system is trapped in a state of perpetual collective frustration. This conflict prevents a simple, orderly alignment, and as the material cools, this disordered state becomes locked in, or quenched. Physicists in the 1970s, including Sam Edwards and Philip Anderson, recognized that this was not just messy magnetism. It was a fundamentally new phase of matter, where randomness itself was the defining stable property. But to truly understand it, they needed a new way to map its behavior. To visualize the behavior of such complex systems, physicists use the concept of an energy landscape. Any physical arrangement of a system, from atoms in a metal to planets in a solar system, has an associated energy level. One can imagine this as a vast, hilly terrain. A system's state is like a ball placed somewhere on this terrain, just as a ball will always roll downhill to find the lowest point. Any physical system will naturally evolve toward a state of lower energy. This universal drive toward minimum energy is a foundational law of thermodynamics, and the key that would eventually unlock a new approach to artificial intelligence. The standard tool for sketching these landscapes for magnetic materials was the Ising model, a simplified grid of arrows that can point only up or down to represent atomic spins. The rules are simple. Arrows pointing in the same direction as their neighbors have low energy, while those pointing in opposite directions have high energy. For a simple magnet, this creates a smooth landscape with two deep valleys, one for all spins up and one for all spins down. But what did the landscape of a spin glass look like? In 1975, physicists David Sherrington and Scott Kirkpatrick developed a model that provided a stunning answer. By allowing every spin to interact with every other spin with random strengths, they discovered that the energy landscape of a spin glass was not a simple bowl. It was an extraordinarily rugged, mountainous terrain riddled with an immense number of valleys, each of varying depth and separated by peaks of different heights. Each valley represented a different stable, low-energy configuration for the system, a different way for the frustrated spins to settle into a frozen, disordered state. This discovery was a turning point. It meant that even a system governed by simple rules, when combined with randomness and frustration, could generate a landscape of enormous complexity. This principle, where intricate global behavior arises from simple local interactions, is known as emergence. The physicists studying these strange metals had, without realizing it, created a perfect mathematical metaphor for a system that could hold many different stable states. The question that lingered was what, if anything, these countless energy valleys could represent outside the world of physics. It would take a physicist searching for a new kind of problem to see in them a model of the human mind. By the late 1970s, John Hopfield, a prominent condensed matter physicist at Caltech and Princeton, felt he had exhausted the problems in his field that matched his interests and talents. He began searching for what he called the problem, something truly fundamental. He found it in the greatest of biological mysteries, how the mind emerges from the brain. Hopfield decided to focus on a specific, solvable piece of this grand question: associative memory. He drew a sharp distinction between the memory of a conventional computer and that of a human. A computer's memory is like a vast warehouse of numbered boxes. To retrieve a piece of information, you need its exact address. If you are off by a single digit, you get the wrong box or no box at all. Human memory works differently. The scent of cinnamon might instantly bring back a flood of memories of a grandmother's kitchen, a complete sensory experience triggered by a single partial cue. This is associative memory, where a fragment of a pattern can dynamically reconstruct the whole. This was the phenomenon Hopfield set out to model. In a landmark 1982 paper, Hopfield unveiled his solution. He had a crucial realization. The mathematical description of a network of interconnected neurons, which can be either firing or on or resting or off, was formally identical to the Ising model of atomic spins, which can be either up or down. The strength of the connection, or synapse, between two neurons was analogous to the strength of the magnetic interaction between two spins. This meant that a neural network, just like a spin glass, must also have an energy landscape. This insight was the conceptual leap. If a neural network had an energy landscape, then the act of learning a memory could be framed as physically sculpting that landscape. Hopfield devised a method inspired by a principle in neuroscience that states neurons that fire together, wire together, to adjust the connection strengths between his artificial neurons. This process effectively dug a valley in the energy landscape at a location corresponding to the pattern he wanted to store. Each memory was a distinct valley. The act of recall then became a physical process. If the network was presented with an incomplete or noisy version of a memory, say a picture of a dog with half its pixels missing, Its state was placed on a slope of the Dog Valley. From there, the network simply did what any physical system does. It evolved toward a lower energy state. Neurons flipped their states one by one, and the network's configuration rolled downhill until it settled at the bottom of the valley. In doing so, it reconstructed the complete, pristine image of the dog. This computation was not a series of logical instructions. It was the natural, dynamic evolution of a physical system seeking equilibrium. Hopfield's model was a brilliant proof of concept, but it had limitations. Like a ball rolling down the nearest hill, the network could sometimes get stuck in a shallow, incorrect valley, a phenomenon known as a local minimum. A few years later, Geoffrey Hinton, then at Carnegie Mellon University, and his colleagues introduced a crucial refinement. They added the physics concept of temperature to the network. In a physical system, temperature corresponds to random thermal energy, which allows particles to jiggle and occasionally jump over small energy barriers. By injecting a controlled amount of randomness into the Hopfield network's updates, Hinton created what became known as a Boltzmann machine. This randomness allowed the network to escape from those shallow, incorrect valleys and explore the landscape more thoroughly, giving it a better chance of finding the deepest, most stable ones. This addition did more than just improve memory recall. It allowed the network to learn the underlying statistical patterns of the data it was shown. Instead of just memorizing and recalling specific images, a Boltzmann machine could learn the general idea of a cat. It could then generate a completely new image that, while not identical to any it had seen, was still recognizably cat-like. This was one of the earliest forms of generative AI. A simplified version of this model would later provide Hinton with the key insight needed to train deep neural networks with multiple layers, solving a problem that had held back the field of AI for years and directly paving the way for the deep learning explosion of the 2010s. The foundational ideas were now established. These networks, born from the physics of disordered matter, could remember, reconstruct, and even generate. Their full power would only be realized when their core principles were applied to create the most advanced artificial intelligence models ever created. The 2010s saw the rise of a new AI architecture that would come to dominate the field: the transformer. First developed for machine translation, it proved astonishingly effective at handling all kinds of sequential data, especially human language. Its success was the engine behind models like OpenAI's GPT series. At the heart of the transformer is a component called the attention mechanism. In simple terms, attention allows the model to weigh the importance of different words in a sentence when processing any single word. When reading the sentence, "The tired fox jumped over the lazy dog," to understand the meaning of jumped, the model learns to pay more attention to fox than to the or over. This ability to dynamically create a web of contextual relationships is what gives transformers their remarkable fluency and coherence. In 2020, a group of researchers made a startling discovery. They demonstrated that the mathematical operation at the core of the attention mechanism was functionally equivalent to the update rule of a modern continuous state Hopfield network. It revealed that the two fields, one driven by engineering and empirical results, and the other by theoretical physics, had convergently evolved to the same mathematical solution. This suggests that this structure is a fundamental and perhaps optimal way to process associative information. The upgrade from binary to continuous states and from a quadratic to a nonlinear energy function grants these modern networks an exponential storage capacity. This immense capacity is what allows the attention mechanism to store and navigate the nearly infinite web of relationships present in human language, a feat far beyond the reach of the original model. This discovery did more than just explain the success of existing models. It opened the door to designing new ones with physical principles in mind from the start. This marks a shift in the field of AI, moving from a phase of empirical alchemy, where researchers tried different architectures to see what worked, toward a more principled phase of physics and chemistry, where models are designed based on well-understood theoretical foundations. Leading this charge is a new architecture called the energy transformer, developed by Dmitry Krotov of IBM Research, Benjamin Hoover, and their colleagues. Instead of the conventional stack of dozens of transformer layers found through trial and error, the energy transformer uses a single, recurrent block that is explicitly designed to minimize a carefully engineered energy function. The computation in an energy transformer is an iterative process. It starts with an initial state and repeatedly updates it, with each step guaranteed to lower the system's total energy until it settles into a stable, low-energy fixed point. This process is directly analogous to a Hopfield network finding the bottom of an energy valley. This deliberate, iterative refinement is seen as a potential path toward a form of System 2 thinking in AI, akin to the slow, logical, and deliberate reasoning humans use for complex problems, as opposed to the fast, intuitive pattern matching that characterizes most current models. The ideas born from spin glass theory are also part of a larger, rapidly growing field known as physics-informed machine learning. The central idea is to build AI models that do not just learn from data, but are also constrained to obey the known laws of physics. These models, often called physics-informed neural networks, or PINs, are trained on two objectives simultaneously: match the available data and not violate fundamental principles like the conservation of energy or momentum. The most significant advantage of this approach is data efficiency. A standard neural network, if tasked with predicting the trajectory of a thrown ball, would need to see millions of examples to implicitly learn the laws of gravity and air resistance. A pin, however, is given the equations of motion from the start. This physical knowledge acts as a powerful regularizer, dramatically reducing the amount of data needed to arrive at an accurate solution. This is essential in many scientific and engineering domains where collecting large data sets is prohibitively expensive or simply impossible. This approach is a direct response to a core weakness of the big data paradigm. Models that learn purely from correlations in data are often brittle. They can fail unexpectedly when confronted with situations outside their training experience. Because the laws of physics are causal and universal, embedding them into AI is an attempt to build models that have a more robust, causal understanding of the world, models that know why things happen, not just what tends to happen. The applications are already making an impact in the industry. In advanced manufacturing, pins can be used to optimize welding processes and predict thermal distortions in 3D printed parts. In the energy vertical, they can create virtual flow meters for oil wells or help design more efficient heat sinks for electronics. In aerospace, they model the complex fluid dynamics of air flowing over a jet wing, reducing the reliance on computationally intensive traditional simulations. But the tech's got its hurdles. Teaching these dual-objective models can be tough, and they might not be great at precisely modeling super turbulent or chaotic stuff. Getting them to scale up and handle a bunch of different physics laws interacting at once is still a big, ongoing puzzle. Our hunt for the hidden order in spin glasses gave us the ideas to create a new kind of AI. As we keep baking the universe's basic rules into these thinking machines, the coolest question isn't what they'll do, but would there still be things they can not do?